Okay, so we're looking at tutorial 3 and part 10 here. We're asked for the specific strength and briefly comment on the meaning of the result. Okay. So when we say specific strength, what we mean is the strength to weight ratio. We'll assume that this is related to the tensile strength, given that it's the only value of strength that we're given. Okay, so the equation for specific strength, and if this is tensile, is equal to the tensile strength over the density. Okay, and no matter what you're asked in terms of specific, so if it's specific yield strength you're asked for, then it's yield strength over density. If it's specific elastic modulus, then it's the elastic modulus divided by density, etc. Okay, so essentially this is a strength to weight ratio. So we can take our 220 megapascals divided by our density, which is 1200 kilograms per meter cubed. And if we calculate that out, it'll give us 0.183. So we can use units megapascals per kilogram per meter cubed, if we like. And we could simplify that if we wanted to give it 183 megapascals per megagram per meter cubed. What you'll find is that in the literature, when you go to look and to compare values, you will find a lot of them given in values of kilonewtons per meter, or kilonewton meters per kilogram. And let me explain where that comes from. Wipe this out for a minute. You know what? I'm just going to wipe this out as well. No, I won't. Okay. Let me take another color here. Okay, so if we take this for a minute, bring it down here. So the base units for this, base units for the stress here are newtons per meter squared. And that's divided here by kilograms per meter cubed. Okay. So if we put all that on the same line, it's all even. Newtons by meters squared minus 2 because it's below the line, and by kilograms to the minus 1 again because it's below the line, and then this meters cubed is below the line, comes above the line, so it's going to be meters cubed. Okay. So that's the base SI units for this. So these then cancel these, and we end up with newtons per meter per kilogram. Okay. So we could represent this as equal to 0.183 newtons per meter per kilogram. It would be the same thing. And if we want to make that a little bit simpler, we could say 183 kilonewtons per meter per kilogram. Okay, and that's how you'll usually see it presented. in the literature. But essentially, these units and these units are equal. Okay. So if we have a look then at what materials typically come out at. So just pick some common ones. So stainless steel is typically 63 kilonewtons per meter per kilogram. An aluminium alloy comes out in and around 115 kilonewtons meters per Kelvin, or sorry, per kilogram. Titanium comes out as 76. Nylon, which one would expect is going to be a lot weaker, comes out as 69. That's interesting. So it's actually quite close to titanium, but of course it's a lot lighter than titanium. Let's have a look over here. So polypropylene comes out as 89. And they're the same units, okay? Carbon fiber. This is the carbon fibers themselves. Come out as 3911. Okay, so that's a very high strength to weight ratio. However, of course, it's very difficult to use carbon fiber on their own. So carbon fiber epoxy composite comes out as 785. Okay, so it's still very high, but not quite as high as that would indicate. And then graphene, if any of you have heard of this material, making lots of noise these days, comes out as 62453. It's a very high strength to weight ratio. Now, using that material might be a little bit more difficult, but then just take a ceramic, for example. Ceramics are a little bit more difficult to characterize in terms of tensile strength. So this figure you might take it with a little pinch of salt, but that's silicon carbide is equal to 1088 kilonewtons per meter per kilogram, which is relatively high as well. Okay, so what have we got here? We've got something that's higher than steel, higher than aluminium, higher than titanium, and so it's quite a high value. Okay, 183. Not probably as high as some of the ceramics, but